third type of energy. We are going to be looking at springs and Hooke's law in relation to our elastic potential energy. So our goal for today is that we'll be able to solve for this energy stored in a spring. So as a reminder, elastic potential energy, that's going to be the energy stored in the stretch or compression of a spring. Okay. And we'll calculate that elastic potential energy by doing 1/2 kx squared, where k is our spring constant, and that's going to tell us the stiffness of the spring. So how easy or how hard it is to deform that spring. And x is going to be the distance that the spring is either compressed or stretched from equilibrium. So a main part of solving for this energy then is going to be that spring constant k. Okay, that's going to vary from spring to spring, and it's going to tell us how much force is required to either stretch or compress that spring. So one way we can solve for that spring constant is by looking at our force versus displacement graph. Okay, we're here that displacement x, that's how far our spring is either stretched or compressed. So if we wanted to write an equation for this line, remember we do our typical y equals mx. So here our y variable is our force. We have some value m as our slope. And then x here would be x, okay, which is the distance or that spring is either stretched or compressed. If we were to get our slope here, what we would do is do y over x. So when we look at our units, it's going to tell us how many newtons are required to stretch that spring per meter. And what's key here is that the force required to stretch that spring per meter, that is our spring constant. Okay, so our spring constant, this guy has units of newtons per meter. Okay, so it's what force is required to deform that spring per meter. And we can find that spring constant by solving for the slope of a force versus displacement graph when looking at a spring. Okay, and this relationship right here, that our force is equal to that spring constant times how far that spring is either stretched or compressed, this is going to be what we call Hooke's law. Okay, it's that relationship between force that we require to stretch the strain versus how far we want to deform it. Displacement graph to write our equation for Hooke's law. So force is equal to that spring constant times how far that spring is either stretched or compressed. If we think back to earlier lessons, we also know the area of that force versus displacement graph is equal to our work that we are doing. Okay. And remember, if you think back to last Friday, the work, that is how much energy we are either adding to our system if we're doing positive work or removing from our system if we do negative work. So the area is equal to our work, but it's also going to tell us how our energy is changing. And if we are looking at elastic potential energy, that's going to compare how much elastic potential energy we end with versus how much we begin with. Okay, so the area of that force versus displacement graph not only tells us our work done, but it's also going to tell us the change in elastic potential energy. How much is our energy increasing by, or how much is the energy decreasing by? Stretched 50 centimeters from equilibrium. The graph below shows the force required to deform the spring. Okay, so we want to find the spring constant for the spring. So remember what we were talking about earlier. We know Hooke's law is our force equal to that spring constant times our displacement. So here, if we look at this graph, that spring constant K, that's going to be the slope. So if we find the slope of this graph, that will tell us our spring constant. So to find our slope, we need to pick 2 points. So here we'll start at 0, 0, because when we applied 0 newtons of force, our spring was stretched 0 meters, and 0.5 and 50. Okay? Because when we applied 50 newtons of force, our spring was stretched 0.5 meters. Okay. So remember, to get our slope, we want to do rise over 1, so do y2 minus y1 over x minus x1. So when we look at these 2 points to get our slope, we'll do our 2 y's, or the difference between those 2 y values, so how high it went up. So 50 minus 0 divided by how far we went over, or the distance in those x values. And here we'll find our slope has a value of 100. But remember, our slope, we need to include units with that. So if we do y over x, to get those units for slope, we'll do our y units of newtons over x units of meters. So this spring has a spring constant of 100 newtons per meter, or we would need to apply 100 newtons of force to stretch the spring 1 meter. So then in part B, we want to find how much work is required to stretch the spring 50 centimeters from equilibrium. Okay, so a big idea here is if we want to find the work done from a force versus displacement graph, I'm going to use blue and orange today because Eli and I are Big Ten champs. Woot, woot. Okay. But our work done in this graph, that's going to be equal to the area underneath the curve. Remember, the area, that's always from our curve to the x-axis. Okay? So here, if we look, we have this nice triangle. So remember, our area for a triangle, that would be 1/2 base times height. So here, we would do 1/2 times our base, or our x value of 0.5, times our height, or a y value of 50. And we would find that we had to do 12.5 joules of work in order to stretch the spring 50 centimeters from equilibrium. Okay. So that is what our work done here would be. Centimeters from equilibrium, we would need to add 12.5 joules of energy. Okay. And we wanted to make sure we converted those centimeters to meters, since we always want to use units of meters in our equations. So then in part C, we want to see how much work is required to stretch the spring an additional 50 centimeters. There's 2 ways we can do this. So we want to see how much work we need to do to stretch the frame from 50 centimeters to 100 centimeters. So the first way is we could find the area of our force versus displacement graph again. However, we don't have any data past 50 centimeters. Okay, so we might need to use a different relationship here. So we know our work is also equal to our change in energy, or how that final elastic potential energy compares to our initial elastic potential energy. So if we want to find the work done, we can find the difference between how much elastic potential energy we end with versus how much we started off with. Okay? Where our final displacement is going to be 100 centimeters, or 1 meter, and our initial displacement was our 50 centimeters, or 0.5 meters. So here would say our work is equal to our final elastic potential energy, so 1/2 K, which we found to be 100, times our final displacement squared, minus our initial potential energy, so 1/2 K, times our initial displacement. Okay? And we would find, in order to stretch this spring from 50 centimeters to 100 centimeters, we would need to add 37.5 joules of energy. Notice how to get the second 50 centimeters of elongation, we would have to add more energy than the first 50 centimeters. Okay? That's because as our spring is already displaced, it requires more and more force, or more and more energy, to stretch it out even farther. Okay? So it'll require more energy to stretch that spring an additional 50 centimeters compared to when we stretched it from the beginning. Okay? All right. So I hope this helps. Please let us know if you have any questions. Otherwise, I hope you have a lovely day.